Good morning, everyone. Welcome to our presentation. Today, we will be discussing gas chromatography. I'm Prachi Jadhav, and along with my team members Rohan Jadhav, Vaishali Jadhav, Sanskruti Jagalpure, and Tanmay Jagdale, we are excited to share our work with you. Our presentation is guided by Dr. Aishwarya Balap from P's Modern College of Pharmacy, NIGD. Over the next few minutes, we will cover the fundamentals of gas chromatography, its applications, and its significance in the pharmaceutical field. Let's get started. Now, let's take a closer look at the detector in gas chromatography. The detector is a crucial component because it's responsible for identifying and quantifying the substances as they exit the column. Essentially, once the sample components are separated, the detector tells us what they are and how much of each is present. There are different types of detectors, each suited for specific applications, but their main job is to produce a measurable signal corresponding to the analytes. This signal is then recorded, allowing us to analyze the composition of our sample. So, understanding how the detector works and choosing the right one is key to obtaining accurate and reliable results in gas chromatography. Gas chromatography detectors play a crucial role in converting the analyte compounds into signals that we can actually detect and measure. Without these detectors, it would be nearly impossible to analyze the components separated by the GC. What's really important to understand is that these detectors are not all the same. They differ in sensitivity and selectivity. Sensitivity refers to how well a detector can pick up even tiny amounts of a compound, while selectivity is about how well it can distinguish between different compounds. These differences directly impact the applications we choose for a particular analysis. As we move forward, keep in mind that selecting the right detector is key to obtaining accurate and meaningful results in gas chromatography. Mass spectrometry, or MS, is a really powerful tool that chemists and researchers use to analyze samples. It works by determining the mass-to-charge ratio of ions, which allows us to identify and measure the amounts of different compounds present. The core idea is that when we introduce a sample into the mass spectrometer, it gets ionized, meaning we add or remove electrons to give the molecules a charge. These charged particles, or ions, are then fragmented into smaller pieces if needed. The instrument then measures these ions based on their mass-to-charge ratio, or MZ. This process gives us two key types of information. First, qualitative data, which tells us what compounds are present. And second, quantitative data, which reveals how much of each compound is in the sample. So, in essence, mass spectrometry helps us identify and quantify compounds with high precision, making it an essential technique in many scientific fields. This ties into the overall theme of understanding complex mixtures at a detailed molecular level. Now, let's walk through how the workflow of mass spectrometry actually works. First, the sample that elutes from the GC column enters the ion source via a transfer line. Once inside, it undergoes electron impact ionization, which is a process that knocks electrons off the molecules, creating ions and fragments. These ions then move into the mass analyzer, which is often a quadrupole ion trap. Here, the ions are sorted based on their mass-to-charge ratio, or M. After sorting, the ions are detected by an electron multiplier, which converts the ion signals into an electrical signal. This signal is then used to generate a mass spectrum, where the peaks correspond to different fragments at specific MZ values. This entire process allows us to analyze complex mixtures with high precision, linking back to our overall theme of detailed molecular analysis. Mass spectrometry, or MS, is renowned for its exceptional sensitivity and specificity, which makes it extremely valuable across many scientific fields. It's particularly powerful when it comes to identifying unknown compounds and analyzing complex mixtures. Now, let's talk about the instrumentation features. First, there's the ion source, often using electron impact, which ionizes the sample. Then, we have the quadrupole ion trap or other types of analyzers that sort and detect these ions. The electron multiplier detector amplifies the signals, making even trace amounts detectable. And finally, a computer system processes the data to generate chromatograms and mass spectra, giving us detailed information about the sample's components. Moving on to the advantages, MS is considered the most powerful detector used in gas chromatography. It provides precise molecular identification, which is crucial when distinguishing similar compounds. It also helps resolve overlapping peaks in complex mixtures, improving the clarity of our analysis. And of course, its high sensitivity and specificity mean we can detect and identify substances at very low concentrations with great accuracy. As for applications, MS is everywhere. It's used in drug testing to detect pharmaceuticals and their metabolites. It's essential for pesticide analysis in agriculture and for monitoring environmental pollutants. It also plays a key role in impurity identification, ensuring product purity, and is heavily relied upon in forensic investigations to identify substances involved in criminal cases. So overall, MS is a versatile, powerful tool that enhances our ability to analyze and understand complex chemical data across many fields. Now, let's talk about the sensitivity of mass spectrometry detectors. They are incredibly powerful tools, offering unmatched sensitivity in detecting compounds. In fact, they can identify trace amounts of substances that might be just parts per billion or even trillion. This high level of sensitivity is what makes MS detectors so invaluable, especially when dealing with complex samples where targets are present at very low concentrations. Whether we're analyzing environmental samples, biological fluids, or intricate mixtures, the ability to detect such tiny quantities really opens up a lot of research and application possibilities. This capability ties directly into the overall theme of how advanced detection technologies enhance our analytical precision and expand what we can discover. The flame ionization detector, or FID, plays a crucial role in gas chromatography. It's primarily used to detect organic compounds, which are often the analytes we want to identify and quantify. The way it works is pretty interesting. The analytes are burned in a hydrogen, air flame, and this combustion process produces ions and electrons. These charged particles generate an electrical current, which we can measure. The magnitude of this current is directly related to the amount of organic compound present in the sample. So essentially, the FID translates the presence of organic molecules into an electrical signal that we can analyze. This makes it a highly sensitive and reliable detector, especially for organic compounds. Connecting this to our overall theme, it highlights how gas chromatography, combined with detectors like the FID, allows us to efficiently analyze complex mixtures and identify specific compounds with precision. Now let's take a closer look at how the flame ionization detector, or FID, actually works. Essentially, the GC effluent, that is, the mixture coming out of the gas chromatograph, enters a flame fueled by air and hydrogen. Once in the flame, the organic compounds in the sample undergo pyrolysis, which means they break down due to high temperatures. During this process, ions and electrons are formed. These ions are crucial because they generate an electric current. A potential difference, or voltage, is applied across the detector, which collects these ions. The stronger the ionization, the greater the current produced. We measure this current using a picoammeter, and importantly, this current is directly proportional to the amount of analyte, or the organic compounds, present in the sample. This proportionality is what makes FID so powerful for quantifying organic substances. As the concentration of analyte increases, the ion production increases, leading to a higher current that we can precisely measure. So, in essence, the FID converts the combustion of organic compounds into an electrical signal that tells us exactly how much of each compound is present. The flame ionization detector, or FID, is known for its high sensitivity when it comes to detecting hydrocarbons. It's especially useful in situations where you need to pick up even trace amounts of organic compounds. One of the key strengths of the FID is that it remains unaffected by non-combustible gases like nitrogen, carbon dioxide, or water vapor, which can often interfere with other detection methods. However, it does have some limitations. For example, it requires hydrogen as a fuel source, which is flammable and needs careful handling. Also, Keep in mind that the sample is actually destroyed during the detection process, so it's a destructive technique. Importantly, the FID is not suitable for inorganic gases or for measuring carbon dioxide and water vapor. This makes it ideal specifically for hydrocarbons, but less versatile for other types of gases. Overall, the FID offers very high sensitivity, a stable baseline with low noise, and a wide linear range, making it a powerful tool in analytical chemistry. But, as with any technique, it's essential to be aware of its limitations, especially regarding the need for hydrogen and its inability to detect certain gases. The thermal conductivity detector, or TCD, operates on a pretty straightforward but powerful principle. It measures how the thermal conductivity of a gas mixture changes. Essentially, when different gases pass through, their ability to conduct heat varies, and the TCD detects those differences. This makes it a very versatile detector because it can identify a wide range of analytes without needing specific modifications. It's considered a universal detection method, which means it can be used for many different gases. This flexibility is particularly useful in complex analyses where multiple components need to be identified and quantified. So, in the context of our overall theme, the TCD exemplifies how we can use fundamental physical properties, like thermal conductivity, to achieve reliable, broad-spectrum detection in chromatography. Now, let's take a closer look at the thermal conductivity detector, or TCD. This detector uses a dual-cell design, which makes it quite versatile because it can detect a wide range of analytes. However, it's important to remember that its sensitivity is generally lower compared to some other detectors. The design involves two separate cells. One is the reference cell, which contains only the carrier gas, and the other is the sample cell, which contains the carrier gas plus the analyte we're interested in detecting. This setup operates on the Wheatstone bridge principle, allowing precise measurement of changes in thermal conductivity. As for how it works, the core component is an electrically heated filament made of materials like platinum or gold. The carrier gas, such as helium or hydrogen, has high thermal conductivity, which helps keep the filament cool under normal conditions. When an analyte vapor enters the sample cell, the overall thermal conductivity of that cell decreases because the analyte typically has lower thermal conductivity compared to the carrier gas. This reduction in thermal conductivity causes the filament's temperature to rise, which in turn changes its electrical resistance. These resistance changes are then detected and recorded, allowing us to quantify the presence of the analyte. So, in essence, the TCD measures how the thermal conductivity of the gas mixture changes due to the analyte, providing a universal detection method that, while perhaps less sensitive, offers broad applicability in various analyses. Now, let's take a look at the advantages of this detection method. First, it's a universal detector, meaning it can identify both organic and inorganic compounds. This versatility makes it very useful in a wide range of applications. Another key benefit is that it's non-destructive, so the sample can be collected after analysis without damage, which can be quite valuable in certain situations. Additionally, it's simple to use and inexpensive, making it accessible for many labs and industrial setups. However, there are some disadvantages we should keep in mind. Its sensitivity is lower compared to other detectors like FID or ECD, which means it might not detect very low concentrations of analytes as effectively. Also, the signal it produces depends on factors like flow rate and concentration, so careful control and calibration are necessary. Because of this, it's not the best choice for trace-level analysis where detecting very small amounts is critical. As for applications, this detector is well suited for analyzing permanent gases, light hydrocarbons, industrial gases, and for process monitoring. Its broad applicability makes it a valuable tool in various industrial and environmental contexts. Overall, understanding both the strengths and limitations helps us decide when and how to best use this detection method in our work. The electron capture detector, or ECD, is a highly sensitive device used in analytical chemistry. It works by utilizing a radioactive source to detect specific compounds. The key idea here is that it measures the presence of electronegative compounds, those that have a tendency to capture electrons. In practical terms, this means the ECD is especially good at detecting substances containing elements like halogens, chlorine, bromine, iodine, plus groups such as nitro groups, peroxides, and quinones. These compounds are particularly electronegative, making them prime candidates for detection by this method. What makes the ECD so powerful is its ability to detect very low concentrations of these compounds, which is crucial in many environmental and pharmaceutical analyses. Overall, the ECD connects to our broader theme of sensitive detection techniques, highlighting how we can identify trace levels of important chemical species with precision and reliability. The electron capture detector, or ECD, is renowned for its ultra-high sensitivity, which makes it especially useful for detecting halogenated compounds and environmental pollutants. Despite its impressive capabilities, it does face some challenges, such as being sensitive to oxygen, which can affect its performance. So, how does it work? Well, it uses a radioactive emitter, typically Ni-63 or tritium, to produce electrons. These electrons are then carried through a detector in a pure carrier gas, usually nitrogen. The system maintains a constant electron current, which serves as a baseline. When an electronegative compound, like a halogenated pollutant, elutes into the detector, it captures some of those electrons. This electron capture causes a decrease in the current. So, essentially, the amount the current drops is directly related to the concentration of the analyte present. This makes the ECD one of the most selective and sensitive detectors available. Its ability to detect very small amounts of electron-capturing compounds is truly impressive, and it plays a crucial role in environmental analysis and trace-level detection. Overall, the ECD's specificity and sensitivity are what make it such a powerful tool in chromatographic analysis. Let's take a look at some of the key advantages of this detection method. One of the biggest strengths is its ultra-high sensitivity, meaning it can detect incredibly tiny amounts, down to femtograms. This makes it especially effective for identifying trace levels of certain pollutants. It's particularly well-suited for halogenated pesticides, PCBs, and chlorinated organic pollutants, which are common concerns in environmental analysis. So, if you're working on monitoring environmental contamination, this technique offers precise and reliable results. However, there are some limitations to keep in mind. For example, it only detects compounds that are electronegative, which narrows the range of substances you can analyze. Also, because it uses a radioactive source, safety is a critical concern. Strict safety protocols are essential. Additionally, it's sensitive to oxygen contamination, so maintaining a controlled environment is necessary to ensure accurate results. And of course, this system requires regular and careful maintenance to perform optimally. In terms of applications, this technique is particularly valuable for analyzing pesticides, herbicides, halogenated solvents, and persistent organic pollutants, often abbreviated as POPs. These are all significant in environmental monitoring and regulatory compliance. Overall, while it has some limitations, its high sensitivity and specificity make it a powerful tool for environmental analysis. Thank you so much for being here today. I really appreciate your time and attention. I hope the insights we've shared have been valuable and have helped clarify the key points of our presentation. Remember, the ideas we discussed are all about driving innovation and creating meaningful change. If you take anything away from this, I hope it's that collaboration and continuous learning are essential for success. Once again, thank you for your engagement and participation. I look forward to seeing how you apply these concepts in your own work. Have a great day.